All right, I think we can go ahead and get started. So it's a pleasure today to welcome Ryan Endlsey to give our lunch talk. Ryan is a grad student at Arizona working with Dan Stark, and his research is focused on the earliest galaxies and reionization and how those two things connect to each other. And he will tell us today about characterizing massive Z of 7 galaxies in the host ionized bubble. So take it away, Ryan.
All right, thank you very much for that introduction, Andrew. And thank you everyone for tuning in. I'm really excited to give this rather long talk kind of on what I've been working on throughout my thesis. So basically, in a nutshell, what I want to tell you about is this survey we've been doing, both identifying and investigating the properties of the most UV luminous massive galaxies that we can find over a relatively wide area field. So I'm talking several square degrees. So first of all, what I want to do in this talk is just give a little bit of opening introduction. For those of you who may be less familiar in the study of reionization. Next, I'll go on to describing this really large area multi-wavelength survey of these UV bright, massive Redshift 7 galaxies, both exploring their ionizing properties, identifying large ionized bubbles, and then also exploring AGN activity within these systems. And then I'll just conclude and discuss some future directions in this field. So very quickly, when did reionization occur? What is our current view of this? Well, we know from the absorption spectra of very high redshift quasars that reionization was largely complete about 1 billion years after the Big Bang. So you can see, as you're going down to about redshift 5.8, you're starting to see the Lyman alpha and Lyman beta force pick up. And that just tells you that the universe is becoming rapidly more ionized. If you go a bit higher redshift, you can try to figure out, when reionization was roughly at its halfway point. And this is commonly done either through looking at the Thomson scattering optical depth of the CMB, which gives you, the integrated amount of free electrons along the line of sight. But then also you can use the damping signatures from extremely high redshift quasars like redshift 6.5 and 7, where the universe has become substantially neutral, and then you can start actually seeing some curvature in the extreme ultraviolet spectrum of quasars that gives you a handle on the H1 fraction at that epoch. So basically all these observations combined right now is telling us that reionization was roughly halfway complete around redshift 7 to 8, or about 700 million years after the Big Bang. So what do we want to do, going forward with that information? Well, ideally, we want to figure out, what were the, dominant sources driving reionization. We know, from these very wide, basically all sky surveys that UV luminous quasars become extremely rare at these very high redshifts. So those are thought to, not be the dominant drivers of reionization. But what may be the dominant drivers is very high redshift galaxies, the ones that formed within the first billion years of cosmic history. So I just want to quickly touch upon, how we have been able to build a census of redshift greater than 6 galaxies within this community. The main way that one identifies these reionization-era galaxies is through the Lyman break. And this is just simply due to the fact that neutral hydrogen within the IgM is going to heavily absorb flux fluids of the Lyman alpha line. And something that's important to note here is that you need very deep optical and near infrared imaging to be able to identify these redshift greater than about 7 galaxies, because the Lyman alpha break shifts redwards of 1 micron about redshift 7. From HST surveys, there's now been an enormous sample of reionization-era galaxies identified, over 1,000 systems at redshift greater than 6. And what this data is telling us, from both these relatively wide extragalactic fields such as candles and then the Hubble Ultra Deep Field, and then also pushing down the luminosity function as far as we can right now with clustering fields, is that there is a high abundance of relatively faint dwarf galaxies in the reionization era. And it's plausible that those could have driven reionization if you make some assumptions about their ionizing photon production efficiency and their Lyman alpha escape, or Lyman continuum escape fraction rather. But that's kind of where we stand right now. But the key questions moving forward are really, how did these small feeble galaxies reionize the universe? How efficiently did the ionizing photons escape from them? How efficiently did they produce those ionizing photons? And then what we also want to understand about the reionization process is how that happened. For those of you who are perhaps less familiar, the idea here is that the universe was more or less fully neutral, shortly after the Big Bang. And then as, structure formation began and galaxies started producing stars, then those collections of galaxies with reionizing IgM around them, creating these ionized bubbles. But the details of how reionization happens is somewhat encoded in the size and spatial distribution of those ionized bubbles. And this is something that we really want to be able to quantify moving forward. So now I just want to give, a kind of a synopsis on why we want to go to these very wide area fields. And the way I'll do this is just kind of by highlighting what we miss out with just, these relatively narrow pencil beam surveys that HST gives us. So, the Hubble has about a 4 square arc minute field of view. And you can, develop surveys that cover, hundreds of square arc minutes, like the Goods fields within the Candle survey. But even that amount of area is still not well matched to the expected sizes of ionized bubbles at redshift 7. So here on the left, I'm just showing you, one of these 5 of the largest Hubble fields for extragalactic science. And then I'm showing you the expected size of an ionized bubble at redshift 7. And what you can pretty well see here is that you maybe get 1 ionized bubble per each of these fields. And even then, you're not able to fully capture the extent of the ionized bubble, and you're certainly not going to be statistically sampling these kinds of ionized bubbles in these Hubble fields. Another thing that you miss out on with these relatively small fields is the absence of massive galaxies. We expect that the largest ionized bubbles formed around the strongest overdensities in the early universe, which would be expected to be focused around the most massive galaxies. So you're not only missing out on the largest ionized bubbles, but you're also potentially missing out on interesting sites of structure formation, and possibly some sources with interesting AGN activity. Another downfall to, or shortcoming, I guess, of current HST fields is that, you are assembling large samples of these faint dwarf galaxies that you expect to be the dominant drivers of reionization, but your ability to characterize those systems is quite limited just due to their faintness. So, by going to large area fields, you can pick up more of the rare UV luminous population that you can, with current facilities, characterize in fairly good detail via spectroscopy and better understand not only their, global physical properties, but also how efficiently those systems were able to produce and emit ionizing photons. So this is just one example here on the left of a very bright redshift 7 galaxy where you actually detect UV metal line emission C3, and this is telling you something about the stellar populations. And so far, this kind of analysis has not been possible with the relatively faint systems that are generally identified in Hubble fields. So this all motivates, the thesis work that I've been doing, which is going to these wide area fields and doing this full multi-wavelength survey of these UV bright massive redshift 7 galaxies. So, some details about this survey. It's so far really been focused on the 7 degrees squared covered by the wide area cosmos field. So this is about 1.5 square degrees. And then the XMM field, which is covered by about 3 times that of cosmos. So in sum total, they're about 7 square degrees. And just for reference, the individual candles fields are shown here for size comparison, as well as a large ionized bubble, what we expect a large ionized bubble to appear as at redshift 7. And you can see, that with these wide area fields, you're able to much better statistically sample these large ionized structures in the universe. And also, of course, you're going to have a much easier time identifying and then subsequently characterizing rare massive galaxies in the early universe. So, just a quick overview of where we stand right now. So far, we've been able to identify over 100 UV bright redshift 7 galaxies over this 7 square degrees. And in case you're interested in the details, the UV luminosity span 1 to 8 times the characteristic UV luminosity redshifts. We're talking stellar masses ranging from between about 10 to the 9 to 10 to the 10.5 solar masses. I know that may sound relatively, a dwarf galaxy-ish in the local universe, but at these redshifts, that really is picking up the most massive population that we know of at these epochs. And then, star formation rates, we're talking about 3 to 100 solar masses per year. And all this is described in about 5 works that are either published or submitted, all listed here. But, as I progress through this talk, I'll point out which works different conclusions relate to. So something that I want to go through a bit quickly is this unique way in which we have been identifying these redshift 7 galaxies that affords a lot of advantages relative to broadband photometric selections that are typical in like HST fields. So with broadband photometry, what you're really getting here is you're just getting a few samples of the spectral energy distribution in the rest UV. Right. And if you consider a galaxy between redshift 7.2 and redshift 7.4, it's very different to tell the difference between those 2 galaxies just based on this broadband photometry alone, because it results in very little color difference, just because the broadband means that you're just washing out this break over a large wavelength range. But what you can do to really improve your photometric precision and subsequently your ability to characterize these systems is you can add in narrowband photometry. And with narrowband photometry, this really allows you to finely sample the location of the Lyman-alpha break and therefore determine the photometric redshift. So you can see here a galaxy at redshift 7.2. This narrowband is, roughly in accordance with what you see in the near-infrared broadbands. But then a redshift 7.4, that is just the Lyman-alpha break has just redshifted past the wavelength range spanned by that narrowband, and then you see a very clear, prominent spectral break. All right, and that's really giving you precise information on the photometric redshift. And this is kind of illustrated here in this figure on the left, where one can do a selection with narrowbands, which are available in these wide area fields that I've been using, which then affords me a much higher photometric redshift precision relative to traditional broadband dropout selections like are done in the HST fields like candles or Hubble Ultra Deep Field. So for reference, the photometric precision we're talking about here in these wide area fields is about delta Z plus or minus 0.1, whereas the broadband selections are about plus or minus 0.5. So factor 5 improvement in your photometric redshifts. And this affords 3 key advantages. I would say one is that it results in much more efficient spectroscopic follow-up, right? If you know the redshift of the galaxy to higher precision, where the emission lines are going to be to higher confidence. Another advantage is that you can have improved understanding of your galaxy physical properties, and I'll come back to that in a bit, more specifically what I mean there. But also something I want to discuss really quickly, and I'll come back to this later on the talk as well, is that you have a much easier time of identifying extremely red, dusty galaxies. You can imagine that if this UV slope was extremely red, it might just look like a low redshift interloper in the broadband photometry. But if you can pick out this very sharp spectral break with narrowband photometry, you do still know that that very red system is indeed at high redshifts. Again, I'll come back to why that's important later on in the talk. So first thing I want to do is touch upon, how we've been able to use these bright area fields and hence the very bright and massive systems in them to characterize the ionizing efficiency of reionization-era galaxies. Okay. So this is, I would say one of the key open questions moving forward within the next several years is understanding how efficiently reionization-era galaxies were able to produce and emit ionizing photons. And without direct spectra, it's still something that we aren't able to directly do. But one thing that you can do with existing data, and it's quite valuable, is you can use the Spitzer IRAC photometry covering the 3.6 and 4.5 micron bands. At specific redshift intervals, those bands will pick up very strong rest optical nebula line emission. So here I'm showing a galaxy at about a redshift 6.8, where the O3 plus H beta emission in this system is giving you a very strong excess in the 3.6 micron filter. And this is akin, to how local green peas are picked out, right? It's just different photometric bands, really. And what I want to motivate to here is that this is really important because O3 plus H beta emission grants some insight into ionizing efficiency. So what do I mean by ionizing efficiency? Well, I mean both the production of ionizing photons, which we expect to be highest in the galaxies with a large fraction of O stars, systems with young ages or very high specific star formation rates. And another important critical factor is the escape of ionizing photons, right? We want to know how efficiently the Lyman-containing photons from these systems actually leak out into the IGM to reionize the universe. And we expect that this escape of ionizing photons is going to be the highest in galaxies that can drive ionized channels through their interstellar medium and circumgalactic medium. And this is just shown here in this kind of this figure here from Donner's review paper. You can imagine the central starburst, and then you just have, kind of radiative or mechanical feedback that's driving out these ionized channels in the IGM and CGM that allows Lyman continuum photons to escape and not scatter resonantly within that cloud. So why can we use O3 and H beta as a proxy for ionizing efficiency? Well, this has really been demonstrated by work done at lower redshifts. We know from samples of galaxies at redshifts between 0 and 3 that your ionizing photon production efficiency scales positively with the equivalent width of O3 5007 emission. And this then in turn scales with O3 plus H beta. Another thing that we have learned from these low redshift surveys is that a large fraction of known Lyman continuum emitters at these low redshifts do show very strong O3 5007 emission. Things like the green peas identified in Isotov et al. Work, but then also there's been some work from Eros Vanzella's group, and then also the recent extruder sample from Rohan Naidoo's work that have all shown that as you push to higher O3 plus H beta equivalent widths, you're more likely to identify systems with very significant Lyman continuum leakage that have historically been very difficult to identify at these low redshifts, but it does seem that these strong rest optical line emitters appear to be a unique population in the sense that they can drive sufficient Lyman continuum leakage. So what do we find whenever we do this kind of characterization at redshift 7? Again, what I'm doing here is I'm effectively just taking this photometric excess and turning that into an O3 plus H beta equivalent width. And, I won't go through the methods here, but if you're interested, it's discussed in the paper. But what we find here is that a substantial fraction of UV luminous and massive redshift 7 galaxies show extreme O3 plus H beta emission. And whenever I say extreme, I mean rest ring equivalent widths in excess of 1200 angstroms. And this is really only seen, locally in systems like green peas and, things that we know emit Lyman continuum leakage. But if you go to lower redshifts, even redshift 2, we know that this kind of population of extreme O3 plus H beta emitters, they're very rare, effectively absent, right? And what this is telling us is that there's this dramatic evolution and galaxy physical properties as we push to higher redshifts that lead to very strong rest optical nebular line emission that we know from lower redshift studies is consistent with a more efficient production and escape of Lyman continuum photons. All right. And again, I mean, you can just kind of imagine that there's this physical picture where over here in this extreme end, where you have like 20% or so of the redshift 7 population having this efficient ionizing properties, whereas the bulk of your low redshift population is instead systems where we know that Lyman continuum leakage is very inefficient. So something that we can ask here, to see that this kind of physical picture holds up is that we would expect a connection between O3 plus H beta and Lyman alpha if this picture that I've just presented to you is true. And the simple reason for that is that Lyman alpha is a hydrogen recombination line. So if your ionizing photon production efficiency goes up, you would expect your Lyman alpha emission strength to go up as well. So we can test this because Lyman alpha is a very accessible emission line from at redshift 7 from ground-based spectroscopy. So what I've been doing is conducting a MT binospec program from 2018 to present, searching for Lyman alpha emission within these largest samples of UV bright massive galaxies that we identified over the wide area fields. We've observed about 90 UV luminous galaxies to date. We have Lyman alpha detections of about over 30 of them. And I just want to highlight again that this high detection efficiency at these redshifts is, I believe, very well assisted by the precise photometric redshifts that we get out from the narrowband dropout selection technique that we've been employing. So, the question again was, does O3 plus H beta connect to Lyman alpha at redshift 7? And we indeed find yes, this does very well appear to be the case. We are finding Lyman alpha emission that is about 5 times stronger in sources with very strong O3 plus H beta at redshift 7. And this is, reflected both in this, kind of oddly displayed Lyman alpha equivalent distribution as a function of O3 plus H beta equivalent. But you can also just see, based on pure, detection counts of moderate O3 plus H beta emitters versus strong O3 plus H beta emitters. We have far higher fraction of detections, Lyman alpha detections among strong O3 plus H beta emitters at redshift 7 than we do among the moderate O3 plus H beta emitters. So yes, indeed, there does appear to be this connection. O3 plus H beta does appear to be telling us something about the ionizing efficiency of very early galaxies. So we'll do that. So the next thing that I want to talk to you about is how we've been able to use these very wide area fields to assist in our identification of very large ionized bubbles in the very early universe. So again, this is one of the questions that I think the community is really starting to tackle over the past few years is one, just identifying these large ionized bubbles is a task in and of itself. But then also characterizing, the size of it, but then also you want to know something about the kind of galaxy population within those bubbles to better understand how galaxies connect to the process of reionization. So to better explain what I mean by this, here's just an illustration showing you, our theoretical understanding at the moment of how reionization progressed. So in the early stages of reionization, you have a few relatively moderate size ionized bubbles being powered by regions of the early universe that are highly overdense, right? You have a higher density of the galaxies in those regions, you're going to have a higher density of ionizing photons coming out of them as well. That will drive, presumably, the growth of the largest ionized bubbles. And then as you progress through cosmic time, of course, more and more of the universe becomes reionized. Those bubbles grow and eventually overlap, and then you end up with the fully ionized universe we see present day. But the questions that remain unanswered is, what was the size and spatial distribution of ionized bubbles at any given redshift, and what was the connection between bubble size and local galaxy overdensity? We don't know really how strongly galaxy overdensity connected with the size of ionized bubbles in the early universe, and this is very much like a very open question still within the community. So I want to quickly go through how one is able to identify large ionized bubbles. And with current facilities, this is done using Lyman alpha emission. So if you imagine a galaxy, the star here, just a cartoon diagram, within a relatively small ionized bubble, this light blue shaded region here, that galaxy emits Lyman alpha photons. Once those Lyman alpha photons hit the neutral IgM shown here in black, they're going to resonantly scatter and just get more or less completely, the signal will be completely washed out, just because Lyman alpha is a resonant line, is incredibly susceptible to scattering by neutral H1. And this explains why, traditionally there's a very low fraction of Lyman alpha detections at redshifts greater than or about 7. Only about 10% of galaxies are detected in Lyman alpha at these redshifts. But then if you consider, a galaxy sitting in a very large ionized bubble, presumably powered by an overdensity, the Lyman alpha photons emitted from that galaxy are then able to cosmologically redshift into the damping wing of the scattering cross-section and face much less attenuation from the neutral hydrogen by the time those photons reach the outer boundary of the bubble, all right? And therefore, one way that you could identify large ionized bubbles is by searching for enhanced Lyman alpha emission from redshift greater than 6 galaxies in a given volume, right? This volume here, if it's fully ionized, you would expect pretty much all of these galaxies to show enhanced Lyman alpha emission relative to the system. So there have been, several to date reported possible ionized bubbles at these redshifts in these papers here. And then, a couple of years back, we claimed the identification of another where we had 3 extremely close and massive galaxies at redshift 6.8, all showing Lyman alpha detections. All right, and this, this sample of 3 galaxies is very common within the literature. It's quite hard to do this, and even the detection of 3 nearby Lyman alpha emitters at this redshift is a possible signal of a very large ionized bubble. So all these galaxies were contained within a sphere of about 1.7 physical megaparsecs. But what was also interesting is that the surface density of UV bright massive galaxies around this 3 Lyman alpha emitters, this suggested a strong overdensity, right? Just photometrically, we didn't have spectroscopy of all the galaxies in this region. So this was, a region where we thought may very well represent one of these very large ionized bubbles in the early universe being driven by a local galaxy overdensity. But we need to really answer more questions to better determine this. Key questions are, do the 3 Lyman alpha emitters that we identified originally trace a more extended overdensity? And do the other galaxies in their vicinity show enhanced Lyman alpha emission as well? If only these 3 galaxies show enhanced Lyman alpha emission, they may just be special 3 galaxies. But if you see a systematic enhancement in all galaxies around them, that's a really good sign that you're looking through an ionized bubble. So to better, characterize this region, we really need a better handle on the surrounding galaxy overdensity and the Lyman alpha emission within the galaxies in that overdensity. So, excuse me. So what we did is we, looked at the galaxies that we really identify around these 3 Lyman alpha emitters here shown in blue, these 3 right here. We searched in a wider area using that narrowband dropout selection technique to identify redshift 6.8 galaxies in the surrounding region. And what was really interesting is that we found 12 of them in this, I think it's 165 arc minute squared area. And that 12 contrasts with the about 3 to 4 that we expect on average based on the total surface density of sources that we found around there. So, not only are we seeing an overdensity just, right here, but even if we go out to very large scales, of order 5 physical megaparsecs, we're still seeing this substantial overdensity, at least photometrically, right? So what we did then is we conducted this ultra deep Lyman alpha follow-up with MMT Binospec to better quantify the overdensity in this region and better determine the possible extent of the ionized bubble. Again, each of these red circles here is just, one of the candidates where we don't know the redshift of them with exact precision yet to determine if they all, in fact, trace this single large-scale ionized structure. what was really exciting is that we ended up detecting Lyman alpha in 9 of the 10 targeted galaxies in this. And I just want to again reference back to that typical detection rate of about 10% for redshift greater than or 7 redshift 7 galaxies in Lyman alpha. So that alone suggests that something might be rather unique about the Lyman alpha properties of the galaxies in this region. They all have redshift spanning redshift 6.70 to 6.88, and they're all contained within this region that has a radius of about 3 physical megaparsecs. And that 3 physical megaparsecs is close. It's not the absolute largest ionized bubble we might expect to form at redshift 7, but it is a much larger than nominal size ionized bubble that you would expect at redshift 7. Nominally, it's like 0.5 to 1 physical megaparsecs. So this is 30-ish times larger in volume than those kinds of more typical bubbles that you would expect. And by virtue of now having spectroscopic redshifts, we can now say that this region is in fact a highly overdense volume of the early universe. There are more than 3 times the average number of MeV less than -21 galaxies in this region relative to average, which we know from global luminosity functions been very well characterized in other fields. Something else that not surprising given our very high Lyman alpha detection rate is that the Lyman alpha cumulus of galaxies in this region are systematically enhanced by a factor of 2 relative to that typical at redshift 7. And that enhancement by a factor of 2 is consistent with expectations if a very large R3 physical megaparsec ionized bubble is containing all of these systems. So we do in fact think that this is a very strong, very high likelihood of having identified one of these very large ionized bubbles in the early universe using these very wide area fields. For reference, previous ionized bubbles at these redshifts only contain like 3 or 4 galaxies that are confirmed Lyman alpha emitters. Having 9 is a significant jump, but then also just the net expanse of the galaxies and the overdensity is also an improvement relative to previous claimed ionized bubbles at these redshifts. I want to quickly jump into another reason why we're focusing on these very large ionized bubbles, very wide area fields, and that is because, in these candle fields, you're really picking up the kind of typical dwarf galaxy population. But if we want to understand, get a global census picture of what's going on in the very early universe, we also need to consider the rarest, most massive galaxies. What are the systems that, kind of bridge the gap between those dwarf systems? And then also, the really extremely UV luminous quasar host galaxies, but then also the few submillimeter galaxies that have been identified at redshifts greater than 6. So something I want to touch on here is, exploring AGN activity within the sample of UV luminous galaxies that we've identified over these wide area fields. And to quickly, give a bit of a motivation here again is that we have a really good census of quasar activity at redshift greater than 6 from these, surveys covering effectively the entire sky. And those have shown us that, there do exist these 10 to the 9, even 10 to the 10 solar mass black holes within the first billion years of the universe. But we don't have really much of any good idea about what the AGN activity is in more typical galaxies in the Re-Ionization era. And even whenever I say more typical, I just mean like basic massive galaxies, right? These quasar host galaxies we think are the extreme end of some distribution, but the further we can push into the more typical population, the better idea we'll have about supermassive black hole growth within these systems, and potentially even whether those AGN activity within these galaxies might have contributed to reionization at all. So the main way that people have been tackling this question of AGN activity in the very early universe is via rest UV spectroscopy. There have been a few identifications of nitrogen 5 1240 emission in redshift 7 to 9 galaxies. Here I'm just showing you one example. But because this nitrogen-5 emission requires an extremely hard radiation field, most people attribute that to AGN activity. So in sum total, there have been 3 such detections. They're all, in the 4 to 5 sigma confidence range. As a kind of side goal of our MT Binospec program was searching for nitrogen-5 emission within our galaxies as well. I should have noted, all 3 of these previous systems were all identified in HST Candles field, but presumably by going to very wide area fields and sampling more of these rare massive systems, we'll have a better idea of AGN activity in this population. So we identified nitrogen-5 emission within at least 1 galaxy so far. We're still combing through our entire data set. But this is a system that I published in a paper from last year. Here you can see the Lyman-alpha emission, and then it's about a 7 sigma nitrogen-5 1238 detection, and then there's maybe a hint of the 1242. But something that's really critical here is that recently we obtained ALMA follow-up of this system, and we do have a confirmed C2 detection consistent with the redshift from that C2 detection suggests that this nitrogen-5 detection is in fact real. So this is an advancement in previous nitrogen-5 emitters as well, which have not had this systemic redshift confirmation before. So this is the first instance among such low luminosity redshift candidates. Now, something that we noticed in our data set was this very interesting, very interesting system is the easiest way to say it at first. So it is an extremely red object. If you're familiar with terms in UV slope, it's beta minus 0.6. And typical systems at redshift 7 have a beta of about -2. So, it suggests extremely dusty. And also it appears to show this very prominent bomber break from the Spitzer IRAC photometry, suggesting a very massive nature, 10 to the 10.5, maybe even 10 to the 11. And the existence of such a galaxy at these very high redshifts would be quite interesting, especially one that's been identified over a relatively small field of view. So, whenever I say that, I mean that there are, of course, quasar host galaxies that have been identified at these redshifts, but those have identified over effectively the entire sky. Here we're identifying one of these systems within the 1.5 degrees squared cosmic field, right? So in that sense, this is a relatively small field. So to better understand the system, we investigated, the rich, full concoction of data sets, spanning X-ray through radio that exists within the cosmos field to better understand what is this thing. And what we found was really interesting is that this object appeared detected in the mid-infrared, the far-infrared, the sub-millimeter, and the radio. So the radio emission could conceivably be coming from AGN synchrotron emission. And then also we have detections in MIPS and SPIRE, which could be coming from very hot dust emission from a central AGN. Excuse me. And if you put the physical picture of this object together, it suggests that if this thing is in fact at redshift 7, then we're looking at something, like I said before, with a stellar mass of about 10 to the 11 solar masses, has a very high obscured star formation rate of about 1,000 solar masses per year, comparable to known sub-millimeter galaxies at these redshifts. It suggests that it harbors a radio-loud AGN, and that this AGN has a bolorimetric luminosity comparable to those of extremely UV luminous unobscured quasars that we know from all sky fields, that's powered by about 1 billion solar mass black hole. Something that perhaps supports this redshift 7 interpretation is that there is a very strong photometric overdensity of redshift 6.8 galaxies around this system, about 10 times the number on average. And something I want to just quickly highlight again here is that the only way that we weren't, I guess, immediately assuming that this was some kind of low redshift interloper, is the fact that we had a wealth of narrowband photometry available covering the system. And what you can perhaps see here is that these red data points show the narrowband photometry, and it shows a very strong spectral discontinuity over about 250 angstroms in the observed frame. And we ran an extensive test of low redshift models, and we could not find any kind of low redshift model that would reproduce something like this. This really was the most feasible solution from the perspective of data alone. But obviously, the extreme nature of this object raises the question of, well, could this just be some very weird, oddball, low redshift galaxy? So what we did is we conducted a cycle 8 ALMA follow-up program targeting this source, just to see if we could detect C2 emission in it. And indeed, we found C2. So we have confirmed that this is, in fact, some redshift 7-ish object. I won't give you the exact spec Z because we're working on the paper in preparation. But from what we can tell, based on the ALMA data, the C2 and the dust continuum, the properties of the system are perfectly consistent with those of known host galaxies of the most UV luminous quasars at redshift 7. And as I said before, the bolometric luminosity of the AGN implied by the mid and far infrared photometry suggests that it is effectively an obscured version of one of those systems. But of course, the identification of just one of these systems within the 1.5 degree squared cosmos field really raises the question of how common are these systems. Again, it appears to be effectively a very highly obscured, extremely luminous quasar and a sub-millimeter galaxy, effectively. And typically, these kinds of systems are identified across several thousand square degrees, whereas this was only identified in a 1.5 square degree area. All right, so I just want to quickly go through, highlight the conclusions from all this work and discuss quickly some, next steps moving forward and how we can better help answer some questions that I've been raising. So summary point number 1 is just, characterizing the ionizing efficiency of redshift 7 galaxies. This has been really difficult traditionally just due to the faintness of most galaxies in the Re-Ionization era, and just with our current facilities, it's been very challenging to characterize them with nebular emission lines. But what we've been able to do is use the UV luminous nature of the systems identified over very wide area fields to better constrain their properties while at the same time exploiting the narrowband photometry that's available over these wide area fields as well. And what we've discovered is that there is a substantial population of UV luminous redshift 7 galaxies that do show rest optical line emission strengths consistent with efficient ionizing photon production and escape. And of course, next steps are really pushing further down both the stellar mass function and the UV luminosity function with JVST. We'll have a much better idea of what the ionizing properties of systems that are far more common in the Re-Ionization era with JVST, but I do think that this, first look on these massive systems gives us an idea of what to expect. And I think that there is this substantial evolution from lower redshifts, even redshift 2 to redshift 7, where these galaxies become far more efficient ionizing agents. And then, by also pushing further down the luminosity function, you'll have a better idea of the ionizing efficiency of low versus high mass galaxies in the Re-Ionization era, which has recently become a bit of an open question. The other thing that we've been able to do with these very wide area fields is discover a very likely, I would say, a large ionized bubble. It's the largest that we've identified, the most number of Lyman alpha emitters. I do think this demonstrates the ability of these very wide area fields to grant us unique insight into the process of reionization. So next steps are to, identify more of these and characterize them to statistically sample the spatial distribution of ionized bubbles at redshift 7 and figure out their sizes. And also what we want to know is, how does bubble size correlate with galaxy overdensity? I think that's a very critical input into models that try to accurately predict how the universe became reionized. Very quickly, I want to motivate, what we can expect to be done over, say, the next decade as far as this ionized bubble science goes. So up here in the top left, I'm showing you the, roughly representative size and area of the cosmos XMM fields that I've been surveying so far. But then if you consider something like the Roman high latitude survey, that's a 300 times increase in area, combined with a 3 to 5 increase in near infrared depth. And I think having access to the millions of Redshift 7 galaxies that this kind of survey will identify is going to greatly advance our ability to study ionized bubbles and their associated overdensities in the reionization era. And really quickly here, I just want to demonstrate what I mean by connecting to overdensities even photometrically. You can take a given field within the Roman HLS, and you can identify kind of your average surface density field, but then also you can identify these extreme regions of the early universe that pack in a substantially large number density of galaxies relative to average. And presumably those are going to be the regions that will be prime spectroscopic follow-up to test for ionized bubbles. And you can do this with things like MIRMOS. Obviously GMT will be beneficial as well. But I do think that the future in this kind of science is very bright over the next decade or so. And then finally, the last point that I'll get to is we've been using these wide area fields to get a better handle on AGN activity within the reionization era, with the goal of, I guess, characterizing them within the more typical galaxy population, which we did detect nitrogen-5 emission within one of them, suggesting likely a low luminosity AGN. But then also, by virtue of this narrowband photometry, we also discovered and subsequently confirmed with ALMA this extremely massive galaxy that is fully consistent with it being effectively a sub-millimeter galaxy, plus the host of a highly obscure quasar. That's also radio loud. And the identification of this system within 1.5 square degrees to me really raises the question of how common these systems are. Maybe we got incredibly lucky, or maybe these things are relatively well sampled by tens of square degrees. So to answer the question of how common are these things, obviously you just need to go to wider areas. I think the cosmos field that we've been able to look into so far is the real state of the art right now on this very full stretching multi-wavelength view of the emission coming from these kinds of systems. But there is effort ongoing to really push that kind of data set availability over much wider areas, and I hope to be able to utilize them within the next several years to try to better answer the question. And that is my talk. I'm happy to take any questions. Thank you for listening.
Great, thank you very much, Ryan. Really nice talk. And yeah, we do have plenty of time for questions. So if anybody wants to raise their hand. Let's see, Drew, you had a question?
Yeah, thanks for that, Ryan. Is there any evidence from, I don't know, high resolution imaging or something of any of these really bright redshift 7 galaxies being magnified, gravitationally lensed?
Yeah. So I can say that for the, there are a handful of systems where the magnification factor, there's some redshift 2 galaxy, 1 or 2 arc seconds away, that's probably contributing, like, say, a factor of 1.3, maybe 2 in gravitational lensing. But I would say that's more infrequent for these kinds of systems. There was this one galaxy identified by Rebecca Bowler that is incredibly luminous, and that system obviously is pretty well gravitationally lensed. But I would say for most of the systems we have identified, the magnification factor is no more than 50%.
Okay, great. And then one other question on the AGN. I'm not sure if you showed the spectrum or not, but does it cover a carbon 4? Like, can you estimate the black hole mass from some?
So yeah, that's definitely something that I'm interested in trying. The only concern there is both the relative faintness of the source in the UV. It'll be incredibly difficult with even Keck to pick up the UV continuum there. And also the C4 emission is going to be very broad if C2 is telling us anything, like 600 kilometers per second full with CatMax. So I do think that's outside of the limits of Keck, but I do think that this is a great GVST follow-up program that I hope to, really see executed and get a better handle on what this is. Thanks for the question.
Let's see. Bade, and apologies if I'm pronouncing your name wrong, but you had a question?
Thank you. And the pronunciation.
Your audio is not very clear. I don't know if that's just for me, but I can't really hear what you're saying.
Yeah, it's kind of staticky, sorry.
Yeah.
Hello?
That's better.
Okay, yep, sorry. Pronunciation was correct, by the way, thanks. So I do have a couple questions. I guess I'll ask one, and if there's time, I'll ask the other. Regarding the comparison of the strong nebular, optical nebular line emission at the Z of 7 that is observed, and the lower relative emitting population at Z of 2. Yes, this one. I just wanted to ask how much of a handle there is on the dust obscuration at the Z of 2, because I mean, surely the dust properties are going to be much different from those two redshifts.
That's an excellent question that I have not admittedly given really any thought to. I can say that this Redshift 2 work was done using 3D HST data, but I do not know the extent to which there was dust correction done, or even an investigation on the properties of those galaxies. Yeah, I will look into that, because I agree that's a very good question.
Mm-hmm. And is there time to ask the other one? It was just very quick.
Yeah, go ahead. Yeah. Okay.
So I just wanted to, maybe you already said it even, what was the largest physical scale of in physical megaparsec for that Lyman alpha emitter group that was in the wide field observation?
Yeah, so in transverse size, it's 3.5 physical megaparsecs, along RA, and then about 5 physical megaparsecs along deck. But along the line of sight, it's about 8 physical megaparsecs total in distance. So whenever I'm quoting this, where is it here? This R equals 3.2, I'm converting this total volume, rectangular volume, into a spherical radius, just for ease of comparison with, people typically quote bubbles and spheres. Yeah.
Okay, thank you. That's all for me.
Thanks for your questions.
Let's see, Ilva, you had a question?
Yes. Sorry. Okay. Yes, so I wanted to ask a question. I don't know super much about this topic, but I was very curious because you mentioned that there was this very bright, like obscured AGN in the very end with a black hole of about 10 to the 9 solar masses. Was that true? Yeah. So I wanted to ask that, because for me, that seems like a very, very massive black hole. And this is really early in the universe. Does that have any implications for the growth of supermassive black holes? And like from your one object statistics, what can you like constrain?
Yeah, I will say that Xiaoyi Fan is a co-author on the papers discussing this, and he is incredibly interested in this question. So, with regards to it being a very massive black hole in the very early universe, I certainly agree with that, but I do want to highlight that it is not unprecedented. So we do know that the host, the supermassive black holes powering UV luminous quasars, average to 6 to 7, can get up to 10 billion solar masses. There are systems detected there, and there are quite a few identified above 10 to the 9 as well. As far as understanding this in terms of supermassive black hole growth in the universe, I think that there are 2 things to potentially highlight here. One is that if this system is representative, and that's a big leap, I think, at this point, but if this system is representative, then what that would be telling you is that obscured supermassive black hole growth is much more common than unobscured supermassive black hole growth in the early universe. That is actually consistent with results from simulations like blue tides, and there's also been work showing that the proximity zones around UV luminous quasars are much smaller than what you would expect if they had been unobscured for as long as they would need to be in order to grow to the masses that they are. So one explanation there is that they are dust obscured for a substantial fraction of their lifetime, and so those ionizing photons do not grow that proximity zone around them. So, overall, it's kind of consistent with that picture, but I would still say that a factor of like 1,000, ratio of obscured to unobscured, that seems a bit, we need more data to really test that, I think. And then, as far as the innate nature of supermassive black hole growth, if the system, again, is real, it just suggests that there are far more of these supermassive black holes out there in the very early universe than we had thought originally from the UV luminous quasar population. And I am still thinking about what that means. I think Xiaoyi, now that we know this thing is confirmed, is thinking about what that means a lot. But yeah, I think that this is very much an open question that I hope will really excite the community.
Okay, thank you for elaborating. Interesting.
Yeah, thank you for the question.
Let's see, we had a question in the chat from Anna. If you can see that, Ryan. If not, I can just read it out. But
yeah, it was submission. Okay. So, will we possibly measure the full size of a large ionized bubble? I want to highlight, sorry, one second. I want to highlight a couple of things. I don't think I included that figure in backup slides, but about half of this field is going to be covered by Cosmos Web. So Cosmos Web will stretch from about here down to here, I think. So, a fairly large fraction of galaxies within this bubble are going to be contained in Cosmos Web. And also, I should highlight that our binospectroscopy has only been focused on this central-ish region. We have not tested whether there are Lyman alpha emitters out to here, over here, over here, or over here. Right? Our data has so far been restricted to this regime where we know there's a very strong photometric overdensity. So something I think that will be really interesting to do in the future is to expand the spectroscopy over a wider area and transverse size, just to see, is this 3 physical megaparsec could be a lower limit, really. I mean, it could extend out here. We just have not tested that yet. And I think that would be quite interesting.
great, thank you. And I think we have one last question from Peter.
Hey, Ryan, great talk. I had a quick question about, or maybe not quick, but a question about, the prospect of finding more of these bubbles in these larger field upcoming surveys, like this Roman high latitude survey you mentioned. There's been like all this discussion recently in the literature about like whether, this idea put forward by Rohan and others that like maybe the most massive galaxies actually dominate reionization because of their ability to get these high escape fractions for brief periods versus this canonical idea of like lots of small galaxies dominating it. I was just wondering if these sorts of large field surveys and like your prospects of being able to find bubbles in there, if that could like help you constrain the different, like that sort of, the actual, agents driving reionization. Like, would you be able to distinguish that based on like, the number or like the size of those bubbles you're finding, or are those surveys just not large enough? Like, would your statistics not be?
So I guess I hesitate to say that that's going to have much constraining power on like the sources that are actually driving it, because you can imagine, right? If you're observing this, overdensity of relatively bright massive galaxies that you're identifying with Roman, that region is still going to contain a very large number of relatively feeble dwarf galaxies that very well could be, assisting in that as well. Without the ability to really, get a handle on the number density of the feeble galaxies in each of these regions, depending on the size, I don't think you'll be able to really get, I hesitate to say there's nothing you can do, but I don't think that's going to be the end all be all on that kind of thing. I think our best route, honestly, is probably just, doing emission line diagnostics of the ionizing properties of massive versus low mass galaxies, which AUST, I think will be incredibly insightful. Yeah.
Gotcha. That makes sense. Thanks.
Yeah, thank you.
All right. Lots of good questions. So that's great. I think in that case, we can just thank Ryan again for a really nice talk. And thanks everyone else for joining us today.
Thank you, everyone. Thank you so much. Bye-bye.
Thanks, Ryan.
Thank you.
Bye-bye.